Here we're going to consider the ramifications. What's that doing there already? The ramifications of what we've been talking about in the combined first and second laws of thermodynamics in terms of the amount of work that you can get out of a system. And along the way, we'll introduce the introductory chemistry equation, the thermodynamic equation. So let's just see what we're going here. What I want to show is that delta A, or dA, is the maximum work obtainable from a system for an isothermal process, or delta G is the maximal non-PV work from an isothermal isobaric process. All right, so let's look first at the Helmholtz free energy. It would be dG also. So the Helmholtz free energy, let's see, we're going to start from the combined first and second laws of thermodynamics. We'll start with the first law just to rederive that. Change in internal energy is heat transferred plus the heat or the work done on or by the system. We know from the second law of thermodynamics that ds is greater than or equal to dq over t, where the equal sign is for a reversible process and the greater than sign is for an irreversible or real process. Or in other words, dq is less than or equal to t ds. So we put that up in here. So we'll end up with du is less than or equal to t ds plus dw work. All right, let's put TDS over here. So du minus TDS is less than or equal to dW. Now recall that the Helmholtz free energy is defined as U minus TS, so that the change in Helmholtz free energy A is du minus TDS minus SDT. That's almost that. Let's make this isothermal, so this is just du minus TDS, where we said this is an isothermal process. Okay, so if that's the case, we can see we can substitute in du minus TDS. We say dA. So we can say that dA is less than or equal to dW. This is a change in Helmholtz free energy, and this is the work done on or by the system. Now note that, let's see, I'll just reproduce that equation down here, or up here. dA is less than or equal to dW, or delta A is less than or equal to W. Now, if we have a system, here's a system, and we're doing work on the surroundings, and that's what the engineers like to consider, work, how much work can you get out. But from our sign convention, W is less than 0. It's a negative amount of work. The system is losing energy. What this says is the Helmholtz free energy will decrease here, but it has to decrease either equal to or even more than the work done here. For example, if the work done is, say, minus 1 joule, and that minus sign is because we're doing work on the surroundings, this implies that dA has to be less than or equal to 1 joule. So in other words, the internal energy, or the Helmholtz free energy, has to decrease. There should be a minus sign there. It has to decrease by more than 1 joule, or equal to 1 joule for a reversible process. So this sort of says that the best you can do for the Helmholtz free energy is to convert it all into work. Okay? Essentially, that's what you're defining. Internal energy minus TS. That TS is like wasted energy. You can't do work. It goes into entropy. So what this says is that the maximum amount of work you can get out of a system is the change in a Helmholtz free energy for that particular process. But in fact, you can only get the maximum amount of work when dA is equal to Let's see, eraser, okay. When dA is equal to dW, or dW is equal to dA, this is for a reversible process. And you get usually less work out because dA is less than dW for an irreversible or real process. So the Helmholtz free energy is the maximum amount of work you can get out of a system, and the only assumption we did here was isothermal. So that's what we mean by that. It's the maximum amount of work obtainable from a system from an isothermal process. In fact, that maximum amount of work is you can only approach that as you approach a reversible process. And as we said in class, a truly reversible process will take an infinite length of time to accomplish. Let's make the same arguments for delta G, and here we'll have to say constant temperature and constant pressure. All right, so delta D or dG. Okay. I will do the same thing we did for Helmholtz free energy. We'll start with the combined first and second laws. du minus TdS is less than or equal to dW. Now for the Gibbs, what we're going to do is to break this up into PV work, which should be minus PDV, and other work. And that other work will be, let's denote that as dW prime. All right, so we're dividing up the work. So we say that du minus TdS is less than or equal to minus PDV plus dW prime. And this is non-PV work. And we'll learn a little bit in this lecture and certainly the other lectures that this non-PV work is chemical work because we're chemists and Gibbs was a chemist. All right, so let's just go ahead and proceed here. Minus TdS, pull that over here, plus PDV. That is less than or equal to dW prime, that non-PV work. Remember, the Gibbs free energy was defined as H minus Ts, or U plus PV minus Ts. So that dG is du plus PDV plus VdP minus TdS minus SdT. That's equal to, we want to make it equal to this, so that's du minus TdS plus PDV. So what we have to do, we have to get that equal to 0, so constant pressure. And we want to get rid of this one, so this would be constant temperature. All right, so at constant pressure and constant temperature, dG is just equal to this, which we can then just plug up into here. And we end up with this equation that dG is less than or equal to dW prime. So the change in Gibbs free energy is the most non-PV work you can get out of a system is for the Gibbs free energy. And that maximum amount of work occurs for a reversible process. In fact, any real process, the change in Gibbs free energy, the work you'll get out would be less than the change in internal energy, Gibbs free energy. So dG or delta G is the maximum non-PV work that you can get out of a isothermal isobaric process. All right, so that's what work is. Now here, this is the equation you've encountered in introductory chemistry. Delta G is delta H minus T delta S. We can understand that in a little more depth here. Let's do that. So we have G is defined as H minus Ts. So that dg is dH minus TdS minus S dt, and that's equal to dH minus TdS at constant temperature. Constant temperature, this goes to 0. Let's integrate both sides. So if we integrate this, we'll integrate dg. It's supposed to be a g. Let's integrate dH. The integral, the sum of integrals. So minus the integral of t ds. T is a constant. You can pull it out of the integral. G is a state function. It's delta g. This is a state function. H is delta s. Minus t is a constant. T integrate. Oh, geez. Delta h. Time to wake up. Delta h minus t delta s. So there's the intro-chem equation that you probably remember, or maybe you don't remember from introductory chemistry when you talked about thermodynamics. Let's do the same thing for A, for Helmholtz free energy. I don't know if this was actually, I think it was an intro-chem, introducing this U minus TS, so that dA is equal to du minus TdS minus SdT, which is just equal to, at constant temperature, du minus TdS. That goes away, constant T. Or another way to write this is delta A is equal to delta U minus T delta S. Again, at constant temperature, constant temperature. So that's where that equation comes from. All right, so that's it for work and these equations that were introduced ad hoc in introductory chemistry. We now know where they come from, just from the definition.